Which will give the most highest heat of hydrogenation? 1. 1 greater than, 2 greater than, again between 3, 4, 5, which is least stable? Cis is least stable. That will give more heat of hydrogenation. So after cis, trans. After that 1,1 disubstituted. After that tri substituted. After that tetra substituted. Clear? Any doubt? Okay. Now you have to, so far nobody asked a doubt. You have to ask me a doubt. Why 1,1 disubstituted is more than cis or trans, that when compared to 1,2 disubstitution, why 1,1 is more stable? That is one question. So the answer is, in 1,1 disubstitution, the double bonded carbon is sp2 hybridized. Between the two methyl groups, what is the bond angle? 120. Double bonded carbons are sp2 hybridized. They are trigonal planar. So this trigonal planar 120 angle, methyl groups are very happy to be in 120 separation. Now if you want to hydrogenate, they become saturated now. The carbons become sp3. When two hydrogens are added, the sp2 carbons become sp3 carbons, tetrahedral. The bond angle is going to decrease to 109.5 degrees. So when methyl groups are 120, they are very happy. If we hydrogenate, they come close, 109.5. They repel with each other. So they want to be more in 120 angle. That's why 1,1 disubstitution is more stable and give less heat of hydrogenation. So that is the thing. Now write the next heading, reactive intermediates. Reactive intermediates. First you mention number 1 carbocations. Number 2 carbanions. Number 3 free radicals. Number 1 carbocation. Number 2 carbanions. These three I am talking about. Carbocation, carbanions, free radicals. Fourth one you write carbenes. Fifth one also you write benzene. Carbocations are generated by the heterolytic cleavage of CCl bond, carbon chlorine bond, or C-X bond, X can be halogen, in alkyl halides. Carbocations are generated by what? By the heterolytic cleavage or heterolytic bond fission of the CCl bond in alkyl halides. For example, if you write a tertiary butyl chloride, so in SN1, the CCl bond undergoes heterolysis, unequal bond breaking, or heterolysis. Then the carbon will get positive charge plus Cl minus. This is how carbocations are generated. Carbon in carbocation is sp2 hybridized and it is trigonal planar in shape. Trigonal planar. Now the second way of producing carbocations, when alkenes are treated, when alkene is treated with concentrated sulfuric acid, CH2 double bond CH2 plus H2SO4, I wrote HSO4 minus. By seeing this H plus, the pi bond shift towards carbon. H plus will attack this carbon. That resulting one is a carbocation. CH2H is added here. It is ethyl carbocation. Ethyl carbocation is primary because the carbon bearing positive charge is linked with one more carbon. Now, this carbocation which is generated when alkene is passed through concentrated sulfuric acid, it is not happy because it is bearing a positive charge. Then the HSO4 minus says, don't worry, I am coming to you because you are bearing positive charge. I am having the negative charge. I will come and attack you. So that results in CH3, CH2, OSO3H. It is called ethyl hydrogen sulfate. What is the name of this product? Ethyl hydrogen sulfate. Now what the industrialists do, this ethyl hydrogen sulfate is subjected to hydrolysis. H plus OH minus. So this step is called hydrolysis. So because of this hydrolysis, what is the product we are going to get? Ethyl alcohol plus this part become ethyl alcohol. The remaining part is H2SO4. Very good. So finally what we have made? Ethyl alcohol we made. From which compound? From ethene. Ethene to ethyl alcohol. It is industrial preparation of ethyl alcohol. 75% of the entire world supply come from this reaction. Because when ethyl alcohol is not there, these drunkards will die. They will roam on the roads and finally they collapse and die. So whether you are drinking, though it contains 50% sugar, it is simply that dark syrupy liquid, molasses, is left to the fermentation units. In fermentation unit, they keep the molasses in a big tank called fermentation tank, dilute it, yeast, a bacteria is added, temperature is maintained at 25, ammonium sulfate, ammonium phosphate are added. So yeast multiplies and ferment the sugar into alcohol along with the liberation of carbon dioxide. So that's how alcohol is produced by fermentation of molasses. But it is a very small fragment. But most of the alcohol comes from where? From ethylene. Ethylene comes from where? From the petroleum, from the cracking of the petroleum products. Cracking or pyrolysis. The Indian government imports a lot of crude oil from foreign countries. We are importing crude from Russia, from Gulf, from Venezuela also. Because India is a huge country, the oil supplies which are recovered from domestically are not sufficient. Our economy is mostly dependent on importing the oil, crude oil, which is called petroleum. This crude oil comes to different refineries. In the refinery, what they do, the crude oil is sprayed on a very hot surface. In Greek language, pyre means fire or heat. Lysis means breaking up. Pyrolysis. So the long chain hydrocarbons of the crude oil are broken into fragments. So some fragments come in the form of natural, this domestic gas, butane, isobutane. Some fragments will come in the form of kerosene oil. Some fragments come in the form of petrol. Some fragmentation will give diesel oil. Some fragments will give aviation turbine fuel, ATF. That is also one form of kerosene actually, used for aircrafts. So like that, the crude oil which we import from different countries, or directly we can't use because it's very black, thick liquid. It's subjected to pyrolysis. What is pyrolysis? Pyr plus lysis. By using heat, we are breaking the bonds. That's called pyrolysis. Pyrolysis of petroleum or crude oil gives lot of products. It will give butane, isobutane, which is used as domestic gas for domestic purpose gas. They fill in the cylinders. Kerosene oil, diesel oil, petrol, aviation turbine fuel, one more compound called naphtha. Many products are formed. So petroleum industry is a very big industry. Of course, we are also actually government of India want to construct a pipeline from Iran to India to give oil for us, but because of political things that are not materialized, otherwise Iran is ready to supply oil for us. Okay, that is a different story. Now, coming back here, this petroleum cracking or pyrolysis gives ethene as a main product. One of the product is ethylene or ethene. That ethene is not used as a fuel. It is used for producing alcohol. How ethene is converted into ethyl alcohol? Ethene is first passed through concentrated sulfuric acid. What product you are getting? Ethyl hydrogen sulfate. Ethyl hydrogen sulfate is subjected to hydrolysis. You will get ethyl alcohol, sulfuric acid is recovered again. That is the advantage of this. Whatever sulfuric acid you use, you are getting back. Now this ethyl alcohol is used for making many alcoholic beverages like beer, brandy, etc., etc. They are used for making different alcoholic beverages. And alcoholic beverages impose on huge excise duty. Government suppose 1 liter beer costs, let us say 10 rupees for the government. They will put some 100 rupees on that and sell the beer as 110 rupees. So for every beer bottle you are purchasing, government is getting 100 rupees. Like that, every state government is getting huge income on alcohol in the form of excise. Only one state in India so far maintaining for the last 20-25 years alcohol-free state is Gujarat. Gujarat, there is a total ban on alcohol. But when there is a ban, people need more it. Thus, through wrong routes, it can enter into Gujarat state. So most of the Gujaratis, I visit Ahmedabad and Rajkot, they say better the government lift the ban. Government will also get some money. We also get alcohol. We are unnecessarily paying high amount because it is smuggled. It is smuggled into the state. Because alcohol is a habit forming liquid and it is synthesized in the liver. Alcohol is digested in the liver. That's why alcoholics usually will have liver damage. So more and more alcohol you consume, more and more your liver gets damaged. Then finally the liver becomes very hard and tough. Liver, fluffy and spongy liver become very hard. Then doctors call it as cirrhosis of liver. So though liver implantations are there nowadays surgically, but not working out, only 50-50 chances of survival. Thus take care while consuming. So in carbocations, the most stable The most stable carbocation is tricyclopropyl methyl carbocation. Tricyclopropyl methyl carbocation is the most stable due to bent bonds structures or dancing resonance forms. What is this bent bond or dancing resonance? Actually, this triangular shaped cyclopropyl ring have orbital overlap like this. These orbitals overlapped along the lines. They have repulsions. That's why they don't stay here. They just bulge out. They don't be along the line. They bulge out. Actually, they should be like this, but how they are coming out. When they come out, due to bulging, bent bonds, the bond is not straight line. Now it becomes bent. Because of this bent bond, the carbon positive charge will overlap with this bent bond. Like sigma p overlap hyperconjugation. Here not sigma bond, it is sigma bond only, but not hydrogen sigma bond, carbon sigma bond. So this bent bonds, once again I repeat, actually the orbital overlap should be along this line. Due to avoid the repulsions, the orbitals simply bulge out. Okay, here I will write. It should be like this actually. Along the line, the orbital should be overlap. But to minimize the repulsion, these orbitals will overlap like this. Meanwhile, the positive charged carbon p orbital overlap with this. This is called bent bond structures or dancing resonance forms. Because of this, tricyclopropyl methyl carbocation is the most stable. Next point. Carbocations usually undergo rearrangements to give more stable carbocations. Either by or by number one 1,2 hydride shift. 1,2 hydride shift. Number 2, 1,2 methyl shift. Number 3, by ring expansion. by ring expansion. Look at this. What is the IUPAC name of this? IUPAC name easy. Very good. 2,3-dimethyl butan 2,3-diol. 2,3-dimethyl butan 2,3-diol. OL. Actually, this compound popularly in common system, it is called pinacol. Now this pinacol, when treated with H plus, means in the form of H2SO4. Whenever alcohols are treated with H plus, the OH group is protonated. OH says, my dear H plus, I am going to donate an electron pair to you. Then the compound will be CH3, CCH3, COH, CCH3, CH3, OH2 plus. This is called protonated alcohol or protonated pinacol. Here the most important point is, write an important point, very important point. OH group is a poor leaving group. OH group is a poor leaving group. When it is protonated, and becomes OH2 plus, when it is protonated and becomes OH2 plus, it becomes a very good leaving group. It becomes a very good leaving group. So here I am writing good leaving group. So it immediately takes the bond pair and leave as water. So after losing water, now it becomes a carbocation. Here minus water. What carbocation is it is? Is it primary or secondary or tertiary? Very good. It is tertiary because it is linked with 3 more carbons. The C plus is linked with 1, 2 and 3. 3 more carbons. It is tertiary carbocation. Actually, carbocation, if it is tertiary, it is already stable, but still it undergoes a rearrangement. This methyl group on the adjacent carbon is along with the bond pair is shifted to this carbon. It is called 1,2 methyl shift. 1,2 methyl shift. So after methyl shift, now this carbon become plus. And this carbon will have 3 methyl groups now. Now due to methyl shift, the tertiary carbocation becomes now secondary. Very horrible. Tertiary is the most stable. Why this 1,2 methyl shift and converting into a secondary carbocation? The answer is, yesterday we discussed, the lone pair stabilized carbocation is the most stable. Even when compared to tertiary, the lone pair stabilized carbocation is the most stable. So here I am writing lone pair stabilized carbocation is the most stable. Now because of that, the product will be CH3, C double bond OH, O gets plus, CCH3 thrice. Now O don't want to carry positive charge because it's an electronegative atom. So O says, my dear H, you give the bond pair and leave as H plus. Then ultimately what is the product? CH3, C double bond O. CH3, CH3, CH3. This is called a penacalone. Or 3,3 dimethyl 2-butanone. IUPAC name 3,3 dimethyl 2-butanone or but-2-one, which is popularly called as penacalone. The entire rearrangement is called penacol-penacalone rearrangement. What the rearrangement is called? Penacol-penacalone rearrangement. Since we are discussing about the carbocations, I noted a point or mentioned a point that carbocations usually undergo rearrangements. What type of rearrangements? Either 1,2 hydride shift or 1,2 methyl shift, or the third one, ring expansion. Now I am going for ring expansion. Ready? Just commonly asked question I am giving. Now in this, as I already mentioned in the previous example, whenever OH group is there, whenever you are adding H plus or acid, the OH group is immediately protonated. The OH will donate a lone pair to the H plus and you will get a protonated alcohol. When OH is converted into OH2 plus, what happens? It is a poor leaving group, we already mentioned. When it becomes OH2 plus, it is a good leaving group. It takes the bond pair and leaves. Then what you will get is a carbocation. See, there are two possibilities. Simply the H adjacent to that carbon, if it gives its bond pair and lost as H plus, you will get CH2 double bond the ring. This is one possibility. But this is very minor. A small product is formed. Second is, now it is a 5-membered ring actually. 5-membered ring connected to CH2 plus. What happens is, the ring breaks and one CH2 group will migrate to this. Ring expansion now. This ring expansion gives 6-membered ring. This bond breaks, this will link, one carbon will get plus charge. Now one of the hydrogen will give its bond pair and you will get cyclohexene. This is the major product. So when the ring opens, already ring is having how many carbons? 5. When the ring cut and opens, and this will link with this, total how many membered ring? 6-membered ring. So one carbon will get plus charge because this entire bond is broken and linking this. This carbon will become plus. To nullify the plus charge, one of the hydrogen gives its bond pair and loses H plus. Ultimately you will get cyclohexene. This is called ring expansion. Now, we have to discuss one more here. Can I move? What it is? 3-methyl 3-methyl 2-butanol. 3-methyl 2-butanol. To this, I added H plus and heat. So what is the first step whenever H plus is added to a compound containing a OH group? What happens? Protonation occurs. This is a poor leaving group. Leaving group is abbreviated as Lg. Poor Lg means poor leaving group. So after protonation, CH, OH2 plus CH, CH3 twice. Now this is good Lg, good leaving group. So when it leaves the entire with bond pair, so what you are going to get? Minus water, you are going to get a secondary carbocation. Secondary carbocation. But the secondary carbocation is not happy. It sees this hydrogen adjacent to it and asks, my dear hydrogen, you shift along with the bond pair here. 1,2 hydride shift, so that plus charge will come here and you will get a more stable tertiary carbocation. So here I am writing arrow 1, 2, 2 more carbons. By 1,2 methyl shift you are going to get secondary carbocation. By 1,2 hydride shift you are going to get tertiary carbocation. So this is all about some of the important concepts related to carbocations. They are sp2 hybridized trigonal planar with 120 bond angle. So they are generated by the removal of halogen from alkyl halides, or they can be generated by the addition of H plus to alkenes. Carbocations usually undergo rearrangements. What type of rearrangements? Either 1,2 hydride shift or 1,2 methyl shift or ring expansion. So all these are very, very important. Now, heading is carbanion. Carbanion, carbon bearing the negative charge. Carbon bearing the negative charge is called carbanion, in which the carbon is sp3 hybridized and is pyramidal in structure, pyramidal shape. So this is carbanion. Methyl carbanion, sp3 pyramidal. If alpha hydrogen of aldehydes and ketones, next point, if alpha hydrogen of aldehydes and ketones is removed by a base, the resulting one is a carbanion. And aldol condensation is an example of carbanion addition. And aldol condensation is an example of carbanion addition. So here I am taking acetaldehyde, it is treated with a base, its common name is acetaldehyde. IUPAC name is ethanol, AL, not ethanol. Ethanol is ethyl alcohol, this is ethanol. Now this carbon is called alpha carbon. Functional group adjacent carbon is alpha, and it has 3 alpha hydrogens. These 3 hydrogens are alpha hydrogens. So the base, when you add a base, the base want to remove the H, alpha H, in the form of H plus. That's why what the H will do, it will give the entire bond pair to carbon and removed by the OH minus in the form of water. Then ultimately what you will get is CH2 minus CH double bond. You will get a carbanion. Of course, this carbanion is stabilized by negative pi conjugation. What is this conjugation called? Negative pi conjugation. So this is the resonance structure. Actually, it is also called enolate ion. Now the carbanion generated in the first step in aldol condensation aldol condensation. So the acetaldehyde molecule is attacked by the carbanion formed in the first step. So this carbanion will attack the positive carbon or adds to the positive carbon. So this is what we call carbanion addition. It becomes O minus. Now this becomes CH2, CH double bond. Now this will react with a H plus and O minus become OH. Functional group adjacent carbon is alpha carbon. Next one is beta carbon. So it is called beta hydroxy. Beta hydroxy butyraldehyde. Which is popularly called as aldol. The reason for calling aldol, it contains both aldehyde group and vol group. This is called aldehyde group, CHO. This is called vol group. So two groups are there, aldehyde group and vol group. That's why popularly called as aldol. Now in the last step, as aldols are very unstable and cannot be isolated, simply on heating, the OH and H will be removed as water from the adjacent carbons, and the final product will be CH3, CH, double bond CH, single bond CHO. You will get a compound called crotonaldehyde. Actually, this crotonaldehyde is an alpha beta unsaturated aldehyde. After writing crotonaldehyde, write below it is alpha beta unsaturated aldehyde. What is the IUPAC name of crotonaldehyde? 2-butanol or but-2-in-1-ol. IUPAC name of crotonaldehyde 2-butanol or but-2-in-1-ol. So aldol condensation is what kind of addition? It is an example of carbanion addition. So how a carbanion is formed in the first step? The OH minus removes one of the alpha hydrogen in the form of H plus, resulting a carbanion. That carbanion is already stabilized by negative pi conjugation, resulting in enolate ion. That carbanion attacks the second molecule of aldehyde. Write a point here. Condensation essentially involves the formation of new carbon-carbon bond. Condensation essentially involves the formation of new carbon-carbon bond. Actually, stability of carbanions methyl carbanion greater than primary, greater than secondary, greater than tertiary. Stability of carbocations tertiary greater than primary, greater than methyl. Stability of free radicals same order. Stability of carbocation and stability of free radicals is directly proportional to plus I effect and inversely proportional to minus I effect. Similarly, stability of carbanions is directly proportional to minus I effect, inversely proportional to plus I effect. So in the reactive intermediates, under the heading of reactive intermediates, I mentioned carbocations, carbanions, free radicals, carbenes and benzene. So during the reactions of organic compounds, these are the intermediates are in between the reactant and the product. They are formed as an intermediate. That's why they are called reactive intermediates. For example, in aldol condensation, what is the intermediate form? Carbanion. That carbanion adds to the second molecule of the aldehyde, resulting a beta hydroxy derivative, which on heating loses the water and give alpha beta unsaturated aldehyde. That alpha beta unsaturated aldehyde we mentioned as crotonaldehyde. Types of organic reactions. Substitution, addition, elimination, rearrangements. So under again substitution, you have nucleophilic substitution, free radical substitution, electrophilic aromatic substitution. Nucleophilic substitution, yesterday also I mentioned. SN1, SN2, SNI, ARSN. Free radical substitution, not that much varieties. Electrophilic aromatic substitution also, same, only one variety. Addition, three types of additions. Write the first variety. Electrophilic addition. Electrophilic addition. Second variety, nucleophilic addition. Nucleophilic addition. Third variety, free radical addition. Three varieties of addition. Elimination, E1, E2, E1CB. Under elimination, you have to write 3. E1 elimination, E2 elimination, E1 conjugate base mechanism, E1CB. Of course, these are all broadly this many type of organic reactions are there. Yesterday we already discussed about FRS. Dr. Pong. Sit down and answer, no need of standing. In FRS, how many steps are there?
3 steps.
What are those 3?
Initiation, propagation and termination.
Very good. chain initiation, chain propagation, chain termination. We discussed all these. In case of initiation, the covalent bond is equally broken, homolytic fission, resulting free radicals. The attack of free radical on a neutral molecule is propagation. Combination of two free radicals is termination. So Dr. Pong is very active. The easy way to remember names: Dr. Ricky, Dr. Pong, Dr. Tommy, Tommy, Swanky, difficult. So slowly. Dr. Sapasa. Apaka. Apaka is just changed as Sapas. So in 7 musical notes, Sa, Re, Ga, Ma, Pa, Da, Ni, Sa, Sa, Pa, Sa. That's 7 musical notes. Dr. Hitler. Okay, these are all, but we are going to study in haloalkanes, haloarenes chapter. We are going to study all the 4. In alkanes chapter, again we are going to discuss the free radical substitution. In benzene chapter, benzene undergoes EAS. This is abbreviated as EAS. In our syllabus, which molecule undergoes EAS? Benzene undergoes EAS reactions. In our syllabus, which molecules undergo FRS? Alkanes undergo FRS. In our syllabus, which molecules undergo nucleophilic substitution? Haloalkanes undergo nucleophilic substitution. In our syllabus, which compounds undergo electrophilic addition? Alkenes. Or you write under each one point. Here you write haloalkanes and haloarenes undergo. Haloalkanes, haloarenes undergo what? SN1, SN2, SNI, ARSN. So which compounds undergo? Haloalkanes and haloarenes. Under the heading of free radical substitution, alkanes undergo FRS. This is abbreviated as FRS. Alkanes undergo FRS. Under EAS, benzene undergoes EAS. Now, addition 3 varieties. Under the heading of electrophilic addition, alkenes undergo electrophilic addition. Alkenes undergo electrophilic addition. Carbonyl compounds undergo, that is aldehydes and ketones, undergo nucleophilic additions. carbonyl compounds, that is aldehydes and ketones, undergo what? Nucleophilic additions. Free radical additions are found in anti-Markovnikov's addition. Free radical addition where we study under the heading of anti-Markovnikov's, Russian name, Markovnikov's addition. Elimination. E1, E2, E1, CV, all these are shown by alkyl halides. Alkyl halides undergo elimination reactions. That means haloalkanes. Rearrangements. Just now we discussed pinacol-pinaclone rearrangement. That is a common term, not a particular compound. Rearrangements are shown by many compounds. Write the heading, methods of purification of organic compounds. Methods of purification of organic compounds. You have to get pure sample of camphor, and that camphor and given sample are finely ground and mixed, and the melting point of this mixture is determined. If the melting point of the mixture is same that of pure camphor, your sample is also pure. This method is called mixed melting point method. Very, very, very important point. The best way to determine the purity of organic compounds is by mixed melting point method, in which the given sample is mixed with the pure sample and the melting point of the mixture is determined. So what we do in the mixed melting point method, the given sample is mixed with the pure compound and the melting point of the mixture is determined. If the melting point of the mixture is same as that of the pure compound, then the answer is your sample is pure. Purity of liquid organic compounds. Purity of liquid organic compounds is known with the help of their sharp boiling points. Is known with the help of their sharp boiling points. Next, camphor. Next point, camphor.
Can you spell that?
CAMPHOR. Camphor. Camphor trees. Very 60, 70 feet big trees are there, camphor trees. In the entire east coast of India, we have camphor trees. So the bark, the leaves are boiled in water, the vapors are collected, and that is camphor, pure camphor. Of course, it is also artificially made. Two types of camphors are there. One is used in food materials for smelling agent, One is used for religious purpose. In most of the religious traditions, they light camphor, easily combustible solid. So camphor, benzoic acid, camphor, benzoic acid, naphthalene, anthracene, naphthalene, anthracene, 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 iodine, I2, are purified by sublimation. So in one sentence, we mentioned all these sublimable substances. Suppose you see, I finely ground some sodium chloride and camphor, both are white color substances. I finely ground powder, camphor plus NaCl, and gave the mixture to you. I mentioned already, I revealed this white powder form contain both camphor and sodium chloride. How do you separate? I want pure camphor. Very simple. You take that in a porcelain dish, the given mixture, invert a funnel on that. The funnel is closed with a cotton bud. The funnel is wrapped with ice cold cloth. Simply the porcelain dish is heated. So in the mixer, only camphor sublimes, change into vapors. NaCl won't change into vapors. These vapors go into funnel because the funnel is wrapped with a ice cold cloth. Immediately they condense and sublime. So the funnel you take and scratch, all the camphor you will get. That is one sublimable and a non-sublimable. Two are separated by the process called sublimation. Write the second point. Crystallization technique is used to remove the soluble impurities from a given organic compound. From a given organic compound, crystallization is used to remove the soluble impurities in a given organic compound. When the compound is dissolved in a suitable solvent in hot condition, when the compound is dissolved in a suitable solvent in hot condition and subjected to cooling. So I'll explain this. Crystallization is a technique of purification. So in crystallization, what we do? We dissolve a given organic sample in a suitable solvent in hot condition. So in hot condition, the compound is soluble, some impurities also soluble. So all are soluble. Now you got a solution. Here selection of solvent is very important. In hot condition, impurities are also soluble. The organic sample is also soluble. But on cooling, impurities remains insoluble the compound, pure compound remains insoluble, and on cooling, crystals of the fresh pure compound are separated, which are removed by centrifugal action. Like I told you, the sugarcane juice is subjected to centrifugal action, where sugar crystals are separated. Similar technique. Here a hot solution made in a suitable solvent is subjected to cooling. The pure organic compound crystallizes out. Soluble impurities remain in the solution. This is called crystallization. 1 minute. Next point. If two liquids narrowly differ in their boiling points, if two liquids narrowly differ in their boiling points, they are separated by fractional distillation. They are separated by fractional distillation. Example, benzene and toluene. Second example, the different components of the light oil fraction, light oil fraction of coal tar, TAR, coal tar, COAL, coal, TAR, coal tar. Haven't you heard about the word coal tar? When coal is destructively distilled, you will get a thick black viscous liquid called coal tar. Coke is left behind. So that is called fractional distillation. One more example you write. Water, H2O, bracket, boiling point 100 degrees centigrade. And heavy water, D2O. Water is H2O. What is its boiling point? 100 degrees centigrade. And heavy water is D2O, capital D. D2O, deuterium oxide, within brackets boiling point 101.42 degrees centigrade. 101.42 degrees centigrade. That means water and heavy water differ by a boiling point of only 1.42 degrees centigrade. That type of narrow difference, the compounds are separated by what? Fractional distillation. Liquids which decompose before they reach their boiling points are purified by distillation under reduced pressure, or purified by distillation under reduced pressure, or vacuum distillation. Example, glycerol. What is the impact now of glycerol? Propane 1,2,3 triol. IUPAC name of glycerol is propan 1, 2, 3 triol. It is a trihydric alcohol. Glycerol and hydrogen peroxide. Next point, liquids which contain a high boiling liquid mixers which contain a high boiling component and a low boiling component. Are separated by steam distillation. Steam distillation example, a mixture of ortho and para-nitrophenols. A mixture of ortho and para-nitrophenols. Ortho-nitrophenol is steam volatile with low boiling point. Para-nitrophenol is steam non-volatile. Write that point also. Ortho-nitrophenol with low boiling point is steam volatile. Para-nitrophenol bracket high boiling point is steam non-volatile. One more very important point. In steam distillation, the vapor pressure of steam plus the vapor pressure of volatile component is equal to atmospheric pressure. Next point, if the organic compound is already present in aqueous medium, it is extracted by adding a suitable organic solvent. Which is immiscible with water. When the mixture is thoroughly stirred, the organic compound passes to the organic solvent layer. The organic compound passes into the organic solvent layer, leaving behind the aqueous layer. Leaving behind the aqueous layer. This is known as differential extraction or solvent extraction. This is known as differential extraction or solvent extraction. Okay, some organic compound you have extracted in aqueous medium. It is already present in aqueous medium, water medium, but you want to recover it from water. Add its own friend, organic solvent, and that organic solvent should be immiscible with water and thoroughly shake or stir. So after thorough shaking, the organic compound already present in aqueous medium says goodbye to aqueous medium. No, my friend came. I don't want to stay with you. Organic solvent is my friend. I am an organic compound. We both like each other, and it passes to the organic layer. Aqueous layer is left behind. Two separate layers you can see. That method is called differential extraction or solvent extraction. The technique of, next point, adsorbing. The technique of adsorbing different components of a mixer. The technique of adsorption, not absorption, ADSOR. The technique of adsorption of different components of a mixer on a suitable adsorbent. A suitable adsorbent is known as chromatography. Is known as chromatography. So actually I will give a little introduction about chromatography. Actually, a Polish botanist, not a chemist also, a botany scientist from Poland, he first invented this technique called chromatography. What he did, he has taken burette. The burette is filled with chalk powder. Chalk pieces are powdered and packed in the burette. Now this burette is called a column. The chalk powder packed in that is an adsorbent. What is the difference between absorption and adsorption? You already know. Absorption is a bulk phenomenon, completely absorbing, like a sponge you dip in water. Absorption. If you dip chalk in water, only the outer layers become wet. Inner part of the chalk becomes dry. Still remain dry. So if absorption is restricted to surface, it is called adsorption. So what the Polish botanist, what he did, his name is Sweat, T-S-W-E-T-T, T silent, T-S-W-E-T-T, Sweat is a Polish botanist. He packed the burette with chalk powder and he extracted the chlorophyll from the plants, from the green leaves. And this chlorophyll pigment with a solvent is poured into the burette, which is packed with chalk powder. The different components of chlorophyll are absorbed as different color bands. So in a glass burette, we have seen different color bands. Chrome is related to color. We call it as chromatogram. Different color bands are separated. And the technique is called chromatography. So chromatography is a separation technique, first of all. Chromatography is what? A separation technique. And it uses the principle of adsorption. Now, though it was discovered by a Polish botanist, later a lot of development has occurred in this, and different type of chromatography techniques were developed. Now you have, if you go to any big industry, you have HPLC machines costing very lakhs of rupees, high performance liquid chromatography. So whenever they want to separate the components, there is a capillary tube. You take the sample and put the capillary tube in that sample. It will suck that sample, go into the machine. Machine will separate everything. Practically you need not do anything. Just simply keep the beaker under the machine. It will give a printed chart also about which components are there, what are the molecular weights, everything. That type of instrumentation techniques came into chromatography. So chromatography is a very important industrial tool, a separation tool. First developed by Sweat, a Polish botanist. Okay. Now, under the heading of chromatography, adsorption chromatography is divided into two types: column chromatography and thin layer chromatography. Adsorption chromatography is divided into two types: column chromatography and thin layer chromatography. See the same thing, whatever I said, column chromatography, burette is taken as a column. So in column chromatography, burette is a column. A suitable adsorbent like silica gel or anhydrous alumina. In column chromatography, there is a stationary phase, a mobile phase. Stationary phase is the substance that is filled in the burette. Sweat filled what? Chalk powder in burette. Now what we are filling in the burette? Anhydrous alumina or silica gel, right at point. In column chromatography, the stationary phase contains anhydrous alumina, Al2O3, or silica gel, SiO2 dot XH2, are used as adsorbents. The liquid mixture to be separated is placed in the column. The liquid mixture to be separated is placed in the column. above the adsorbent. And a suitable solvent within brackets. Here the solvent is called with a special name called eluent. E-L-U-E-N-T. And a suitable solvent within brackets eluent. E-L-U-E-N-T. Eluent. E-L-U. Letter E. L-U. E-N-T. Eluent. Bracket close. Is poured in excess. The components of the mixer move to different distances. Move to different distances. See these three diagrams. First one, solvent or eluent is placed on the top. Mixture of compound A plus B plus C. Below that, adsorbent, stationary phase. A glass, wool or cotton is kept at the bottom so that it won't entirely drain out. So when the solvent is poured, first it is separated into A and B plus. But by adding more and more solvent or eluent, A, B, C, three separate parts, they get separated. This is called column chromatography. In column chromatography, normal burette is taken as a column. The column is packed with a suitable adsorbent. That is called a stationary phase. What is the stationary phase or suitable adsorbent here? Silica gel or anhydrous aluminum. Actually, silica gel is a fine powder. It goes into the lungs. That's in the lab, whenever we want to fill the column, we wear a mask and fill with silica gel. Normally, you should not do. It goes into the lungs and cause irritation, respiratory irritations, asthma, bronchitis, all this. So, here the mobile phase is the solvent. Two phases are there in column chromatography. One is a stationary phase, that is adsorbent. The other is mobile phase. What is the mobile phase? Suitable solvent or eluent. Solvent or eluent is the mobile phase. Next. In thin layer chromatography, TLC, in thin layer chromatography, what is the abbreviation for that? TLC. A glass plate is coated with silica gel or alumina. Silica gel or alumina. Now, a sample containing mixture of components. A sample containing a mixture of components is placed as a dot on the TLC plate. on the TLC plate on the base line. The entire TLC plate is just dipped in a suitable solvent. Dipped in a suitable solvent below the baseline. Below the baseline. The different components are adsorbed on the TLC plate and move to different distances. The relative adsorption of components is determined by a factor called retention factor or retardation factor. Retention factor or retardation factor. Here you see this RF, retention factor or retardation factor. The retention or retardation factor is given by this formula. Please write this formula. RF is equal to distance moved by the substance from the baseline. Distance moved by the substance from the baseline within bracket x by distance moved by the solvent from the baseline, that is y. Okay, I will explain like this. Let us say this is a TLC plate. A glass plate will be there. This plate is coated with a suitable adsorbent like silica gel or anhydrous aluminum. Now on this plate, we write just with a pencil a line called baseline. We write a baseline. Just above the baseline, we put a dot of the sample. With a capillary tube, just we put a dot. That sample contains XYZ or ABC components. Now this entire TLC plate is kept in a small dish containing a suitable solvent. Just below the baseline. It is just dipped in the solvent. Due to capillary action, the solvent moves. The solvent just touching the plate, it moves above the plate along with the adsorbent. Adsorbent is stationary. While just moving it, it touches the sample dot. Sample dot contains different components. Each component will move to different distances. So if there are colored dots, you can see on the plate different colored dots at different heights. If they are not colored, we keep this entire TLC plate in a UV chamber. UV chambers are there in the lab. We open the door and keep this and switch on the UV, and from the above we see. UV light irradiate, each spot appears a bright spot. That is one way. But UV light is extremely dangerous. That's why you have to be very cautious. You should not spend too much time under UV light. It causes cancers. UV is one way helpful, one way dangerous.